Okay, so welcome everyone. Today we have Ying Tong, who's our guest speaker in this series. So Ying, the mic is yours. Welcome.
Hi, thank you for having me. So, I'm a research associate at Geometry, and today I'm gonna talk about the Groth16 proof system, and actually the later half of it. So, when we have a quadratic arithmetic program, how do we go from there um, using pairing-based cryptography to get the Groth16 snark? So I'm going to put the link to my slides in this Zoom, and I'm going to share my screen. Can you see my screen?
Yes.
Okay. So I understand that you've already covered sort of the first part of the Groth16, which is going from the computation to R1CS to the QAP. So we won't spend too much time on that. We'll just do a recap. And then this session will take us from QAP through the linear interactive proof and finally to our snark. And you can interrupt me at any time for questions. So starting with the recap, this circuit should look very familiar to you. It's the is0 circuit in Circom. And so the idea is we can represent every operation in this circuit, every multiplication and addition as a fan-into arithmetic gate. So for example here, -1 times n equals some variable that we'll call W2, wire 2. And we just, and this defines our first gate, gate 0. Its left input is wire 1, its right input is -1, and its output is wire 2. And we just keep going. The next gate is another multiplication gate. And the next gate is an addition gate. And the last gate is the multiplication gate that produces our output. So yeah, this is how we get from a computation or a program to an arithmetic circuit. And from the arithmetic circuit, we can get this flattened constraint system known as the rank 1 constraint system. So once we have our R1CS, we can massage it into a quadratic arithmetic program. And just to give it away a bit, the quadratic arithmetic program has this form. So yeah, AZ, BZ equals CZ, where A, B, and C are matrices, and Z is the satisfying assignment. And it's called quadratic because of this operation here between AZ and BZ. So how we get the R1CS into the QAP is, first of all, we lay out all the wires, and for each gate, we lay out the left, right, and output variables, and we mark which wires are involved in the left, right, and output variables. So for gate 0, left input, and the right input is a constant, -1, and the output is wire 2. and we do this for every gate. So you should be familiar with this free addition gate. So when we have an addition gate, we actually represent it as W4 plus 1 times 1. So in other words, W4 plus 1 fits in the same row. It fits in this, it's all considered the left input, and the right input is 1 here. So in this sense, addition gates are free. You can have W1 plus W2 plus W3 times something else. It won't cost you anything in terms of an additional gate. And so we do this for all the gates, and we sort of collect all the left inputs into this A matrix. So see, this is the first row from each of these gates. And we collect the right inputs into the B matrix and the outputs into the C matrix, and then we expect that given some satisfying assignment Z, that this check should hold. And this is our QAP. And so this ends our recap. So from this point, the question is, how do we efficiently check this QAP? So how we do this is we encode the QAP, first of all, as a polynomial identity. So from a matrix identity to a polynomial identity. And we do this by noticing that this matrix vector product can be represented as a linear combination of the matrix columns. So basically, we're using our witness as the coefficient for each respective matrix column. So it'll be the sum Z0 and the A0 column, Z1, A1, and so on. And basically then we can encode each of these columns as a polynomial using the fast Fourier transform. So I'm not sure how familiar we are with AFFT. I'm just going to go through it quickly for completeness. So yeah, given each of these columns, given A0 to AN minus 1 in your matrix column, how do we encode this column of values as a polynomial? So the trick is to think of these column values as the evaluations of a certain polynomial. So let's say A0 is the evaluation at x0, A1 is the evaluation at x1, and so on. This is the polynomial we want to construct. And for efficiency, for the fast Fourier transform, we pick these evaluation points to be actually the powers of some root of unity. So this is just an optimization. And then we can then express our polynomial as a linear combination of the Lagrange bases. And the Lagrange bases are these very useful polynomials that evaluate to 1. So for each Li evaluates to 1 at omega to the I and 0 otherwise. So effectively, this lets you select just the coefficient you want at each I. So yeah, you get this polynomial with the desired behavior that at omega 0, it evaluates to precisely A0, and at omega 1, A1, and so on. So we encode our matrices as polynomials. And so therefore we encode our matrix identity as a polynomial identity. I'm going to stop here for questions if anyone has any. Is this all familiar?
Yeah, somewhat. We kind of stopped here basically.
Okay.
I sometimes describe this, Yang, I don't know if it makes sense, but I think of the polynomials as an iterator over the gates, and the evaluation points is like you are iterating over the variables. So with x equal 1 and 2 or 3 or someone, you are picking the variable, but with the polynomial, you're picking the gate basically. And then the coefficient is basically just to scale or twist the polynomial to that specific instant, basically. I don't know if that iterator view makes sense.
Yeah, it does make sense. I have it the other way around here, though. Like, I have that each polynomial encodes a variable, and that each root of unity encodes a gate. Let me go back here. So we encode the columns as polynomials here, where the columns are variables, and we evaluate each column at a root of unity, where the root of unity is the gate. I may have gotten this flipped around, but yeah, I also think of it as iterators for sure. So yeah, we should double check which way is which.
No, I think you're right. You said the polynomials iterate over the variables, right?
Yes, exactly.
No, yeah, I think you're right. It's me who got it like switched around. I think you're right.
Okay, yeah. It's also just a matter of convention. You could equivalently just transpose all these matrices. But yeah. So now we have a polynomial identity, and it holds over some evaluation domain D. And what is this evaluation domain? It's precisely our roots of unity. It's precisely the number of gates we have. So at each gate, this identity should hold. So another way to write this statement is that this identity holds. This identity holds mod the vanishing polynomial over D. So the vanishing polynomial is simply the polynomial that evaluates to 0 at all points in D. And so the final polynomial identity that we check is that ax bx minus dx, it equals some multiple of the vanishing polynomial, whereby this multiple is itself a polynomial. So this is another way of saying that dividing this left-hand side by the vanishing polynomial gives you no remainder. It gives you a polynomial. And we call this the quotient polynomial. So this right-hand side is 0 mod the vanishing polynomial. Okay, cool. So now that we have this final polynomial identity, we're going to find out how to efficiently check it. And we're going to start with not Groth16, but Pinocchio. So Pinocchio was an older proof system that Groth16 is an optimization of. And we'll see we'll see why Pinocchio is a good choice to start with. Um, the reason is it does its checks in a very modular way, and we can see clearly the motivation behind each check. Whereas because Groth16 is aggressive with its optimization, um, it's harder to pull apart the construction. So, yeah, once again, this is what the polynomial identity we're checking. And just to remind you, this AX is the linear combination of the AJX column polynomials. Okay. And respectively, so for BX and CX. And the coefficients in the linear combination is your satisfying assignment Z. So to efficiently check this identity, we're going to make use of something called the Schwarzschild lemma. And this is used everywhere in this field. So what the Schwarzschild lemma is saying is really simple. It's saying that if two polynomials are different, then they can agree at most d points, with d being the degree of each polynomial. So to understand why this is true, remind yourself of this really basic fact that a polynomial of degree d has at most d unique solutions. Solution meaning that f at that point equals 0. So if we want to check an identity between two polynomials of degree d, we can just make a third polynomial that is their difference, right? And now we'll check where hx equals 0. So again, hx equals 0 at most d points. In other words, these two polynomials, if they're different, can agree at most d points. If they're the same, then they agree everywhere. Then hx is 0 everywhere. So if they're different, hx equals 0 with probability only d over the size of a field element. There's a typo here. So this is me assuming that you're drawing your x evaluation points from some finite field. So, and usually the degree d is much smaller than the size of the finite field. So for example, in Halo 2, we're working with polynomials of degree, I think 2 to the 11 or 2 to the 12. And our finite field is 2 to the 255. So it's a negligible probability. So this is all to say that to evaluate a polynomial identity, it is sufficient to evaluate it at a random point. And with high probability, you will detect if this polynomial identity does not hold. So that's exactly what we're going to do. For our identity, we're going to pick a secret evaluation point tau. And we're going to make a linear interactive proof whereby the prover sends evaluations of each of these polynomials at the secret point tau. And then the verifier just checks if these evaluations hold. And why this had to be a secret evaluation point is because if the prover knew it in advance, then it could have chosen its witness to manipulate these polynomials to agree at exactly tau. Even though this identity does not hold. So where the elliptic curve pairing stuff comes in is in addressing this problem. So in real life, how are we going to hide this value tau? Firstly, how do we make a secret value tau? And secondly, how do we still allow the prover to perform linear operations over tau? So the prover needs to be able to evaluate their polynomial at tau without knowing what tau is. So this step of going from the LIP to the snark is known as the compilation step. It's compiling a very ideal information theoretic protocol into something real world, and something that is enforced with cryptographic assumptions. So first of all, how do we get a secret value tau? You might have heard of the trusted setup or the perpetual powers of tau setup. This is also known as phase 1 setup in Groth16. So basically, use an MPC multi-party computation to get a random value tau. And in fact, to get all the necessary powers of this tau so that we can evaluate degree D polynomials. And then the output of this setup process is a structured reference string, SRS, that contains just commitments to these powers of tau. So commitments here are basically to commit to tau 0, you take a scalar multiplication of tau 0 with a group element G1. And that's also denoted with this subscript 1 notation. This is the convention we'll use for the rest of these slides. So it is, so let me see. Yeah. Why is it that given just these commitments to the powers of tau, we cannot recover the actual powers of tau? It's because we're working in a cryptographic group. So for Groth16, most Groth16 implementations we're working in an elliptic curve. Actually, yeah, all Groth16 implementations we work in an elliptic curve. And an elliptic curve is a cryptographic group, which means that the discrete logarithm problem is hard in an elliptic curve group. So the discrete log problem is precisely this: is given some commitment to a secret, and given also the public base point used to make that commitment, can you recover this secret scalar? And this is hard in an elliptic curve group. So we feel good about just publishing these commitments to the powers of tau in our SRS. And now what we've achieved, actually, we wanted the prover to do linear operations over this tau, right, to evaluate their polynomials at this tau. So how the prover can do that is, the prover can't quite evaluate their polynomial at tau, but they can compute a commitment to the evaluation at tau. So to see what this means, for some polynomial with coefficients C0 to CD, you can compute the commitment to P evaluated at tau using just a multiscalar multiplication between your coefficients and the pre-computed commitments to the powers of tau. So it's quite trippy because you've computed this commitment to an evaluation at a point that you don't even know. It's kind of a blind evaluation. I'm gonna pause here again for questions. Okay, cool.
How large is D in generally in our ONCS system like Groth16? Is it supposed to be 2?
D is the degree, the maximum degree of polynomial that you can support, and I think, let me see. I think the largest one I've heard of is the Filecoin powers of tau. It's like 2 to the 30 or something like that. So yeah. But basically, these trusted setups are multi-party computations, and it requires a lot of people to participate. So, and each time they do it, they upload the parameters somewhere so that people can reuse it. Uh, yeah. Yeah, I can't find it right now, but it's 2 to the largest I know of is 2 to the 30 something, I think. Um, yeah, so once again, you can't recover the secret given just a structured reference string. So now, using these powers of commitments to powers of tau, and using our ability to do blind evaluations, we can now do our we can now check this polynomial identity at the secret point tau. So to remind you again, we're doing this because of the Schwarzschild lemma, because it's sufficient to check it at a random secret point tau. And we have to introduce this tool called the pairing, the bilinear pairing, in order to actually do these sort of quadratic to do this quadratic identity. So what I mean is, given the blind evaluations, we can compute the commitment to A evaluated at tau, right? Yeah, we can compute the commitment to A evaluated at tau. And similarly for B evaluated at tau. But this identity requires us to multiply these two commitments. And that's not a supported operation in elliptic curve cryptography. You can add two curve points, but you can't multiply them. So to sort of enable multiplication of two curve points, we have to introduce this tool called the bilinear pairing. So E here is a pairing operation. And we'll see in the next slide what a bilinear pairing is. But yeah, this is why we have to introduce a pairing. And by the way, this is also why pairing-based snarks are limited to quadratic gates, because we can't go, like, if I introduce a like dx, for example, then I would need to multiply three things, and a bilinear pairing can't do that. Like we don't know if there's like a trilinear k-linear operation like that. So yeah, on this slide, I'm showing you the pairing form of this polynomial identity check. And we have to introduce several other checks as well. So the well formation check and the coefficients consistency check. And these are to make sure that our commitments were constructed as expected. And we'll go into each of these checks in the next few slides. So a bilinear pairing, this E operation, I realize this diagram looks a little bit crazy, but basically it allows you to do a multiplication in the exponent. So what this means is given 2 points, A times P and B times Q, I can sort of simulate the multiplication of these 2 points by mapping it to a third point in the target group, which is this point. And I'm not going to go into the math of how this works. For us, let's treat it as a black box that allows us to multiply 2 elliptic curve points. And actually, every time you see a pairing operation, you can just convert it in your head to like what this operation looks like in the clear. So A of tau times B of tau is equivalent. So our first check is the main divisibility check. So we're converting this identity directly to the pairing form of it. So A times B minus C times 1 equals ZH. Yeah. So using our powers of tau, trusted setup, we can compute these commitments to the columns of our A, B, and C matrices. So basically, we just do a blind evaluation of each column at tau. And we do this also for the vanishing polynomial Z. And how we're going to use this setup to make our proof is as follows. So we're going to take these evaluations of the A, B, and C matrices, A, B, and C matrix columns, and we're going to compute the linear combinations using our assignment. So if you see in the top right-hand corner here, pi A maps to AX here. It's a linear combination of the AJ columns. So pi A is just AX, but in commitment form, evaluated at tau. And same for pi B and pi C. And same for H. We just evaluate blind evaluation of the quotient polynomial H at tau. And we output these 4 group elements, pi A, B, C, H. Is there a question? Using these 4 group elements, the verifier can check this identity using pairings. So this text in red here should correspond to this divisibility check here, which is the pairing version of this identity here. So yeah, the pairing of pi A and pi B minus pi C times 1 should equal the vanishing polynomial times the quotient polynomial pi H. I'm going to stop for questions. Cool. It's pretty intuitive so far. We're just doing the thing, but in the pairing form. Now, okay. Now we're gonna go into the two additional checks that were introduced, and how we're gonna motivate it is by asking this question. So, given some pi a from the prover, this is just a group element. How do we enforce? How does the verifier enforce that pi a was indeed constructed as a linear combination of the AJ column commitments? Because this is just a group element. The verifier doesn't know the ZJs. So they can't do the linear combination on their own. Yeah, so how are we supposed to know if it's just a completely random group element, or if it was indeed a linear combination of these agreed upon column commitments? So how we enforce this is through this well formation check. So this well formation check basically relies on another assumption called the knowledge of exponent assumption, and we'll go through that in a little while. But first, let's go through the construction. So for this well formation check, we're gonna take the column commitments from SRS1, and we're gonna sample a secret shift alpha A. Yeah, let's just do pi A first. And then we're gonna commit to the column polynomials evaluated at tau once again. But this time, we're gonna actually shift the commitments. So instead of just doing AJ of tau, as we did in SRS1, we now shift it by this secret alpha A. So I'm gonna call this shifted polynomial A prime. So the output of SRS2A here is the commitments to the shifted columns evaluated at tau, and also a commitment to the secret shift that was used. So the prover once again computes a linear combination of these shifted columns using their satisfying assignment, right? So in the last step, it was pi A, now it's pi prime A. And then the verifier checks the relationship between pi A and pi prime A. So the intuition here is that since the prover did not know this alpha A, the only way they could have preserved this ratio between pi A and pi prime A is to have reused the same coefficients Z. Is to have reused the same column commitments AJ. So to make this clearer, this depends on the knowledge of exponent assumption. So given our secret exponent alpha, and given this sort of alpha pair, which is, think of it as our original column AJ and the shifted column AJ prime. Sorry, I'm editing my slides like live. So given this secret exponent and this pair that's shifted by this exponent, um, so, oh, sorry. I think I did a wrong edit to my slides. Equals. Yeah, the point here is that A prime is the shifted version of alpha A. So if a prover is able to return another valid alpha pair, pi A, pi prime A, such that this ratio alpha holds between them, then she must know the ratio between pi A and pi A and A, I think. Okay, I feel like this part of my explanation is a bit confused, but this is called the knowledge of exponent assumption. I encourage you to read up on it and to sort of convince yourself that if this assumption holds, then, and if the prover does not know the secret shifts, then they must have used the same column commitments in pi A and pi prime A. Or in other words, they must have constructed pi A from the correct column commitments in SRS1. Okay, I'm gonna stop here for questions. I feel like I'll get some questions now. Or it was too confusing. I have no questions.
Then maybe this is just a general question. Is there is the knowledge of exponent assumption related to the discrete log?
I think so. Yeah.
Because
actually, yeah.
Sorry, go ahead.
No, you go ahead.
I think I might be mistaken, but I have always thought that it's synonymous because the discrete log, you're just going around the clock a number of times, which is the same thing as raising something to something. But I think I was reading recently there is some subtleties there. I could be way off. I'm just.
I mean, the discrete log assumption is here actually, like given A and A prime. Can you recover the discrete log of A prime relative to A, which is alpha? So, like, firstly, we assume you can't do that. I think maybe this depends on the discrete log hardness. So, assuming you cannot recover this alpha and that you can return another valid alpha pair, then you must know the ratio. Oh, the ratio Z between. My slides were very correct before I edited them live. Yeah, then you must know the ratio Z between pi A and A. So in other words, you must have applied the same ratio Z. Like pi A, pi prime A is just Z times A and A prime. Like you did just a very simple scaling of the original alpha pair. And that's the only thing you could have done if you don't know the secret alpha. So we're trying to enforce this relationship between all the pi's and pi primes here. Yeah, and because both the pi's and pi primes were constructed using these alpha shifted commitments in the SRS, then pi A must have been constructed from these original column commitments.
The one is, sorry, I think you have a subscript there on the slide before. Maybe the one before that. Yeah, here the one is a subscript, I think, in the middle.
Oh yeah, thank you. Cool.
So the shifting,
by the,
Ying, if we can think of sometimes you want to know that the prover knows the evaluation at some point, but now you are making sure that they know a scaling. You know, they if they know how to scale the polynomial in certain, it's as if, you know, if someone knows how to apply just the right force to dunk the ball on a hoop of a height 2 meters, they must know also how to apply just a little bit extra to dunk it in a hoop that is 3 meters or something like that. So they know something. They know the relationship between angle and force on the ball, basically. So the scaling is not about, it's about how much you bend the polynomial or scale a polynomial as opposed to evaluating it at a certain point. This is how it's making sense to me.
Yeah. It's like constraining the form of this commitment to be a linear combination of these very specific columns. Yeah, I think this check is a little subtle. So, by the way, I encourage everyone to look at this paper, BCTV 14. So, this exposition was adapted from figure 10 in that paper, where they go over an improved version of Pinocchio. And they explain a little bit the motivation behind each of these checks. Yeah, or you could also look at the original Pinocchio paper, I think.
Here, sorry, if you go back to that slide again, in number 3, there is no B at the beginning, is there? In number 3, the gray part.
Let me see. Yeah, I think this should be a beta. I don't know why sometimes my... Oh, is it caps lock beta? It becomes a B. I don't know why, but thank you. Yeah, so number 3 is the coefficients consistency check, and we're going to get to that next. Yeah, well formation check. So we use this to constrain that pi A, pi B, and pi C are well formed, meaning that they use the agreed upon column commitments from SRS1. So now the next thing we want to check is consistency across pi A, pi B, and pi C. So each of them are well formed. Each of them, we're convinced, now uses the correct column commitments. But we also want to check that each of them use the same coefficients in this linear combination. So that the witness is reused each time. So I call this the coefficient consistency check. And how we're going to do this is we're going to sample a random secret gamma and another shift beta. And we're going to commit to now the beta shifted versions of the columns. So similarly to the alpha shifted versions. And we're going to output these beta shifted column commitments, as well as a commitment to gamma and beta gamma. And this will become clearer how we're going to use it. So we now compute this sort of sum polynomial fx. So it's the sum of A, B, and C. But multiplied by the corresponding assignment at that point. So yeah, it's just like how AX was the linear combination of the AJ columns using the assignment. So FX is the linear combination of the sum of the A, B, and C columns using the assignment. And then we're going to shift Fx by beta to get F double prime X. And then we're going to use the beta shifted commitments in SRS3 to commit to F prime evaluated at tau. So this should be tau here. And we call this commitment pi double prime F. And this is the perverse output for the coefficients consistency check. And how the verifier uses this is it checks that gamma times pi prime F equals beta gamma times the sum of pi A, pi B, and pi C, which was our proof from the first divisibility check. So I wish I could go more into the intuition of how this works. I think actually the only way to really understand these later two checks, the well formation and coefficients consistency, is to try to attack them and see what happens if these checks are not there. Yeah, which I didn't have the time to do, but maybe we could do this as an exercise. Okay, I will stop here again for questions.
So one of the issues, Ying, that some of the fellows found this week is the issue of constraining public input.
Yeah.
So here that would be in Z, I guess. Is it part of the?
Yes. Yeah, exactly. So Z is your assignment, and I think the first L elements of it are public input. In other words, your instance. And
Right.
the remaining elements of it is your private witness. So actually in this presentation, I've not made a distinction between the public inputs and the witness. But I can point later on to where this distinction occurs and why public inputs are malleable, basically. Yeah, we'll see later. We'll see later on in the verification process why public inputs are malleable. So, okay. Oh, but hold on. I think that public inputs malleability issue is in Groth16. Um, I don't know if it applies here in Pinocchio. I would think it does. Actually, it's a good question. But I can just skip ahead a little bit and show you why it happens in Groth16. So, So I recommend firstly reading this article by the geometry team. So yeah. So the first L elements of your assignment Z are your public inputs, and the verifier actually computes this term by itself with no help from the prover, because these ZIs are completely public, and this is an element from the trusted setup. So the verifier can do this. But the issue is that if your public input isn't constrained by any gate, then each of these terms would evaluate to 0, and this whole term will evaluate to 0. And it does not contribute to this identity. Like there's no way this term could make the identity fail if your public input is not constrained. So that's why there's malleability for public inputs in Groth16 proofs. Yeah, so the common kind of hack to get around this is to just introduce a dummy constraint that always passes. And the effect of that is to make these terms here non-zero, and to bind your proof to the public input used at proof creation. Yeah, but I think actually this just gives you something called weak simulation extractability and not full simulation extractability. Yeah, so I recommend reading this article. Yeah, but for sure this is a commonly known issue. It's like folklore. Child, have you remembered the artificial square constraint? And I think the point of this article was also, that in practice, these attacks are prevented in popular implementations because they bake in some dummy constraint in the backend. So yeah, they bake in this constraint times 0 equals 0. I'm just curious which implementations you've found bugs in for this public inputs malleability.
It is well, it's the code base that we are auditing, and one of the public input is the message hash, which is not constrained. And so the developer's assumption was that this is something that we push to whoever is importing our library. We're not going to add it in circuit. But I think they finally decided to add this dummy constraint as we suggested, just to be safe in case some of the older, I believe some compilers, they don't add that constraint by themselves. So yeah, it just something that came up. But I just want, the reason I ask about it, I just wanted the fellows to make a link between those public input and witness and the equations that we're looking at. It basically, the witness and the public input, they are all embedded in that z vector, right?
Yes, that's correct. Yes. So, yeah, why the public input part of that z vector is treated differently is because, as we saw before, the verifier has access to it and they can compute this term on their own. So it's not baked into the rest of the proof. So that's why it can be malleated independently of the rest of the proof.
Yeah, makes sense.
Yeah.
Thanks.
Yeah. So, yeah, I actually did not distinguish the public inputs from the private inputs in my presentation. So I'm going to keep this page open and we'll come back to it later. But yeah, I just wanted to first go through Pinocchio to give like a intuition for the motivations behind these alpha, beta, gamma elements. So the Pinocchio proof comes down to 8 group elements, or at least this is the improved version from BCTV 14. So you can think of each field element here, so A evaluated at tau, as being compiled into 2 group elements, pi A and the shift of pi A. Yeah, and Groth16 makes an improvement in that it compiles each field element to a single group element. So it doesn't, these shifts are not included in the Groth16 proof. And these 2 extra elements are also not included. It doesn't have the, so Groth16 doesn't even have this 4th field element. It has just 3 field elements, A, B, C, each compiled into 1 group element, pi A, pi B, pi C. Yeah. So that was Pinocchio. And now we're going to go into Groth16. So Groth16 has a different linear interactive proof. So like I said just now, it has only 3 field elements, A, B, and C. So it's a little bit different than Pinocchio. So you can see over here A. In the setup, we have our evaluation point tau as before, but we also have already the shifts alpha, beta, delta. Actually, yeah, alpha, beta, delta. Actually, I don't think delta is a shift. And random delta. So we compute as before A. So previously A was just A tau, which once again is AX is the linear combination of the AJ axis using the assignment as the coefficient. So previously for Pinocchio, A was just A tau. But now Groth16 kind of bakes in the alpha shift here, and also this random R delta, where R is a random element sampled by the prover. And similarly for B, it's B tau, but we bake in beta, and S delta, where S is sampled by the prover. And then C is this more complicated thing that it kind of preempts the cross terms from multiplying A and B. So you can see here, like, there's a beta, A tau, alpha, B tau. There's C tau, which is just as before. And then it also incorporates the vanishing polynomial and the quotient polynomial. And it also has SA and RB directly in here. So this might look very contrived, and it is. Basically, all of this is just so that this check will pass, and the terms will cancel out nice. The cross terms from multiplying A and B will cancel out nicely. So C is just constructed such that this check will pass. So I'm going to stop here for questions.
And is it correct to think about what Groth16 did as baking the shifting and evaluation into one thing?
Yeah. It's like all those three checks is squashed into one. Yeah. So to look a little more closely at this check and why it holds. So on the left-hand side is just A times B, where A and B are here defined. And it's super messy here, but I think, okay, what to note here is that we have A tau, B tau. We have A tau, B tau from here, A tau, B tau. And we have a lot of other junk. These are just cross terms. So on the left-hand side, we have A tau, B tau, and cross terms. And then on the right-hand side is alpha, beta plus delta times C. So delta times C will get rid of this denominator here, right? And we will introduce a delta factor here. But again, in this whole mess, what you should take note of is we have these two terms, C tau. All this should say tau. Yeah. Plus the vanishing polynomial times the quotient polynomial evaluated at tau. And then, so yeah, these two boxes are what we want to focus on. The rest of the junk is cross terms that cancel out. So effectively, if the left-hand side equals the right-hand side, then that implies that A tau, B tau equals C tau plus Z tau, H tau, which is what we wanted to check in the first place. So yeah, the whole Groth16 is just a highly optimized check that incorporates all the shifts and the coefficients consistency checks and ends up with just this final single check. So yeah, I put a note here that the public inputs are elided. So let's see, if we compare this check with the actual Groth16 check, it will look slightly different. So let me just compare it side by side. How am I going to do this? Let's see. Okay. So if we compare this check versus the real Groth16 check, yeah, so AB, right? AB, whoops. AB on the left-hand side is the same. Alpha, beta on the right-hand side is the same. Delta C is the last term on the right-hand side is the same. But my slides are missing this middle term that has to do just with the public inputs, which the verifier can compute on its own. Yeah, so I suppose my slides, they assume that there are no public inputs. Yeah. But basically, including the public inputs, it doesn't change the mechanics of how this works. You're just splitting it at the index L. I'm going to stop here for questions.
This is what you just mentioned, Lynn, is really Yang is really great because it concretely links to something we dealt with this week. So thank you, that was excellent.
Cool.
It's basically just to clarify to the fellows further, like that Z that Yang was highlighting, that is something that the smart contract verifier, for example, should verify as well. Just to make sure that the prover is not presenting a valid proof, but for a totally different instance, basically, because the public input was not enforced in constraint, basically.
Yeah. The thing is, yeah. Is this dummy constraint trick is kind of a hack, in my opinion, in the sense that it's doing something that the proof system wasn't made to do. So if your public inputs were unconstrained, then I would argue that it's a feature and not a bug that you can change your public input. But in many cases, like for the actual use cases and for how people expect the proof system to behave, this is a bug. So people expect that even if their public inputs are unconstrained, that they shouldn't um, be malleable, and you shouldn't be able to reuse a proof for a different public input. Yeah, but I think because it's quite unnatural and because it requires the introduction of some dummy constraints, it's caused a lot of confusion. Yeah. So I also work on the Halo 2 proof system, and someone recently asked if Halo 2 is malleable in the same way. And it turns out it's not malleable because each proof actually contains some commitment to the public instance. So the proof is already bound to the public input used at proof creation. But yeah, there's something. Yeah,
is it because of the accumulation, Yang, you think?
In the Halo 2 case, it's because we hash the commitments to the public inputs into the fiat Shamir transcript. Like that's how we initialize it. So the prover has one transcript containing the commitments to the public inputs. And if someone intercepts midway and changes the public inputs, then the verifier is going to receive the wrong commitments, and the verifier is going to have an inconsistent Fiat-Shamir transcript. So for the whole protocol, the verifier would just be deriving different challenges than what the prover had, and all the evaluations will, all the opening proofs will fail. So yeah, but it's very interesting. Like, I am of the opinion that if your public input is unconstrained, that you shouldn't expect it to be bound to your proof. But yeah, as mentioned, many use cases, like for example, semaphore, um, they want to just bind the public input to the proof and then nothing else, and do nothing else with the public input. Probably in your use case as well, like the hash of the message, you don't want this proof to be reused for hash of some other message. Yeah. But at the same time, you're not constraining this hash of the message anywhere. Yeah, I if you're interested in this, I encourage you to read up on simulation extractability and weak simulation extractability in this paper.
Yeah, I'll definitely share that in Discord as well. So then if you can take maybe 5, 6 minutes to wrap up, and then just we will allow for 2 or 3 questions before we wrap up.
Yeah, perfect. So, yeah, I didn't really break down the Groth16 checks the way I did Pinocchio because it's more tightly integrated. But I think it would be an interesting note to try and deconstruct the Groth16 um, check. But yeah, over here, you can see that the LIP contains just 3 field elements from the prover, each of which is compiled to a single group element. And that's how you get the smallest proof, um, the smallest known proof, just 3 group elements. So yeah, to wrap up, I wanted actually to mention that what we covered today, Groth16 and Pinocchio, are considered generation 1 snarks. So they are very tightly integrated with the pairing based cryptography as a tool. Um, because they need to conceal the secret point, and because they need to do they need to multiply 2 curve points. So you can do nothing else besides use elliptic curve pairings. Whereas modern R1CS based snarks are more modular. So from the computation up to the QAP, the same. But instead of doing an LIP here, they actually check the QAP using a different information theoretic model called the polynomial interactive oracle proof. And the advantage of this is that it can be then compiled with any polynomial commitment scheme. So you don't have to use something that's pairing based. So for example, Fractal uses Fry. I think Marlin does use the KZG commitment scheme, which is still pairing based. But you don't have to. So yeah, and another advantage of this modular construction is that you can conversely you can reuse the same polynomial commitment scheme for different arithmetizations. So besides R1CS, another popular arithmetization is Planck. And so you can just plug it in here in this modular construction. Yeah. But I think the first generation snarks, Groth16, is still the most efficient snark that is known. And that's because pairings are very powerful. Um, and pairings are perfect for quadratic arithmetic program that's like degree 2 constraints. Whereas if you want higher degree constraints, then you shouldn't use R1CS. And um, conversely, if you're not using a pairing based compiler, then you're not limited to degree 2 constraints, and you can use other arithmetizations. Um, so I want to note, though, that there's um, a very exciting new line of work called CQ or CQ Lin that actually goes back to this tight integration of pairings. So they basically make use of the fact that you can cheaply um, multiply two curve points, um, and they exploit that to um, um, construct very efficient lookup arguments and very efficient lin checks. Um, yeah, without ever having to work with, for example, for the lookup table, you never have to work with the actual values of the lookup table as the verifier. Um, you can just work directly with the commitment to the lookup table. So yeah, all this is to say that I think it is very valuable to understand how pairing based constructions work. Um, and yeah, this is my last slide actually.
Amazing. Thank you, Lane. So that was super interesting. Um, I'm wondering if you think this intuition makes sense in comparing LIP and the polynomial commitment based generation one and generation two, basically. So, generation one, we are basically creating a fingerprint with an evaluation and shifting, while here we are making a commitment by the structure of the polynomial itself. It's like you're taking a fingerprint of the polynomial, not as far as a specific evaluation or specific shifting is, but the polynomial as a overall, basically. Um,
Yeah. You decouple it from the cryptographic compiler, or you sort of, yeah, you're using this very generic interface of just polynomials.
yeah,
Whereas in the LIP, like you said, you need to do some very specific checks that uh, cannot be achieved with anything besides pairings.
yeah, and so and because we are not fingerprinting polynomials at specific evaluations, that's why we can get away without trusted setup. Like we don't need trusted setup because we are not um, doing checks based on a specific evaluation on a random point that should be forgotten or should be toxic waste, etc. So this was an amazing talking. It certainly helps clarify a lot of things in my head, and I hope it created a link in the um, with the fellows with what they have been dealing with practically. I think we had a question, just a quick question about when you were talking about Halo 2. A fellow was asking if quote unquote Halo 2 is better. Um, so I guess one advantage is we don't need trusted setup, but in terms of, I guess, in terms of efficiency, as you mentioned, Ying, verification of Groth16 is still much cheaper, right?
Mm, for sure. In terms of verification and proof size, there's nothing that beats Groth16. Yeah. But as you said, Halo 2 doesn't have a trusted setup. And the other big difference is Halo 2 uses the Planck arithmetization and not R1CS. So this allows us to have higher degree gates and which means you can express very complex constraints more cheaply. And another advantage of Halo 2 or these Plonk based arithmetizations is support for lookup tables. And lookup tables are um, very useful in certain operations, such as range checks and basically bit shifting operations, which in R1CS or without lookup tables, you would need to pretty much always do a binary decomposition of your field element. Whereas with lookup tables, you can save a lot. You can just do like maybe 10-bit decompositions or something like that. Um, yeah, but oh, maybe another thing that's interesting is this very new work called CCS, Customizable Constraint System. It's a generalization of R1CS. So instead of having just A, B, and C matrices, you can have as many matrices as you want. And you checking an identity over multi-sets of these matrices. So this CCS, customizable constraint system, um, they actually, um, yeah, it's a generalization for of R1CS, so it supports R1CS. But they also support Plonkish arithmetization in that you can convert with very low overhead from Plonk to CCS. Yeah. So, um,
Yeah, thank you, Ying.
yeah.
We are coming at 12:30. I don't know if Zoom just ends the meeting because that's how much I scheduled for it. I hope it doesn't because we do have a question, but if it does, just want to thank you before it cuts off, Yang. There is a question about whether Groth16 proofs go well, how go well with all sort of computations. I guess they mean this is what you were just talking about, having custom gates, lookup tables. Vanilla R1CS is not good for that, I guess.
Yeah.
Yeah.
The the main limitation is you only have degree 2 constraints. Um, but you can achieve a surprising amount with just degree 2 constraints. I've seen very efficient implementations of big integer arithmetic and elliptic curve cryptography just using degree 2 constraints. Um, I'd say the main drawback of R1CS right now is there's no support for lookup tables, but there are people working on that as well. Yeah. So the two drawbacks are degree 2 constraints and no lookup tables. And so that's less efficient for um, bitwise operations.
Awesome. So I think that's the last question we have. Thank you again, Yang. This was illuminating. We'll share the slides. We'll share the links to the geometry article that you shared. Obviously, fellows are encouraged to stare at the Pinocchio and Groth16 paper. But hopefully this will help them make sense of it better. But there is no way around, leaning into all that fun pairing stuff to finally understand the whole thing. So yeah, thank you, Yang, and thank you, everyone.
Yeah, thank you. And um, if do you guys have the Discord or something? Is it public?
Yes, I'm gonna send you an invite.
Okay, that's
Um,
cool. Like because like I would love to continue the discussion there. And if
yeah,
anyone is like interested in picking apart the Groth16 checks or building more intuition about the Pinocchio checks, which I think I don't have enough intuition about. I would be really glad to explore that with you. And also, another thing I had wanted to do was to look at the Snark.js implementation and inline some code examples. So, if anyone's interested in doing that with me, that would also be cool.
That
Yeah.
would be amazing. Yeah, 100%. I think the fellows would love that. I would love to uh, be involved in something like that. So I'll send you, Ying, an invitation to Discord after the talk, and we'll take it from there. Thank you, everyone.